Let's discuss a question from from theory of machine basically. Okay, so now what we need to find out is the natural frequency. Remember that for theory of machine there are always two kinds of problem that comes in the exam. Either to calculate the natural frequency, or if you have a damping then just write down the differential equation of the damping. So that is another kind of questions that come, combinations of spring and damping. So one kind is finding out the natural frequency of the system, and the second kind is with damping involved, either forced damping. If it is natural damping then they may ask you what is the damping ratio, or derive the differential equation if it is a combination of a spring mass damper. And if it is forced vibration, then given a sinusoidal force, what is the amplitude ratio, transferability, things like that. Okay, so let's begin this problem. So whenever you have these kind of problems when natural frequency is asked, so what you have to do is you have to displace the mass by x. So here is the mass, I displace it by x. Okay, so when I displace it by x, okay, so when you displace it by x, this, the left spring is in tension, so it tries to come back and it tries to pull, so that is kx. The right spring is compressed, so it tries to again come back to its initial state, so it pushes it, so that is also kx. So both of these acts as a restoring forces which tries to come bring back the disk to its normal position. So these are the thing. Okay, now what are the other forces? From the ground you have n, and it rolls without slipping, so there is some sufficient friction which prevents slipping. So as you tries to bring here, there is friction because you have displaced it, your motion is like this, you have displaced it like this, the friction is in this way. Okay, so now this is your, so all the forces you have represented, this is your free body diagram of your disk. So free body diagram of the disk you have written with all the forces. Mg is another force. So now what we need to find out is natural frequency. So for natural frequency, you know that you need to bring your acceleration, okay, in some proportional into, acceleration has to be shown that it's proportional to your displacement, and then this k is nothing but your omega n square. From that we can get this. Okay, so what we do is, so for this we need to just represent all the forces, displace the system by x, represent all the forces, and then you need to write the governing equation of motion. So governing equation of motion, what you do is, I mean here, because there is translation motion involved and there is rotational motion involved, though they are related because it is given that it rolls without slipping, so we'll use that fact. But what we do is we'll do it in a very systematic way, we'll do it in a very short way also. We'll take moments about c. Now for rotational motion, moment about any point, okay, either if a point is at the center of mass or if the point is fixed. Okay, if it is like rotational mechanics, then a rod hinging about an end. So these kind of problems also, so you can always, this equation sigma m is equal to I alpha can be applied at the center of mass, it can be applied at the point where the system is fixed, or it can be applied at the instantaneous center of mass. Now for a disk which is moving in translation and rotation, which is undergoing a plane motion, and if it is pure rolling, remember this is very important, if it is pure rolling, you can apply this equation about the instantaneous center, which is nothing but the point of contact with the ground, only for a pure rolling case. If it is not pure rolling case, you cannot apply this equation. So we will just use this equation because most of the time slipping is difficult to difficult problems to solve. So most of the time it is rolling without slipping on the surface, so you can easily apply this equation about the contact point. Okay, so this is one way of doing the problem. The other way of doing the problem is you apply this equation about the instead of the contact point you apply about the CG. Okay, and also then you need to apply sigma f is equal to ma. So why we are applying about the contact point is that first I have shown that it is valid to apply at this equation at the contact point. Why it is valid? It is valid only for pure rolling, which is the case here. So it is valid to apply this equation about the contact point. The second thing is that we are applying this because the friction and the n which passes through a contact point, that can be eliminated by applying this equation. So that's the idea of applying this. So moments about point contact C will be mg, n and f are passing through it. So kx will, so we assume that okay, so here x, we have displaced x towards right, so velocity is like this and rotation is like this, omega. Okay. Okay, so now clockwise moment's positive, so kx produces anti-clockwise moment, so kx into r is 1 kx and the right side spring is k. So this is the effective moment about C. There's no other moment because everything passes through, all the forces, other forces apart from the spring forces passes through moment C, so we need not apply. Now I of a disk about C is, we need to use the parallel theorem, so I naught is about the center plus mr square into alpha. Okay, so minus kx minus 2kx into r is I naught plus mr square. I naught is of a disk is mr square by 2, so mr square by 2 plus mr square, which is 3 mr square into alpha. So we again write minus 2kx into r, 3 by 2 mr square into alpha. Now how do I relate alpha to x? So that is again, alpha is nothing but your d omega by dt. Okay, remember that because it's a pure rolling, the velocity is related to the, in a planar motion you have two important parameters, the linear velocity and the angular velocity. These two are related for a pure rolling case by radius. Okay, so v is equal to r omega, so x dot is r omega and alpha is d omega by dt, so it is basically, if you differentiate another time, so r omega dot is nothing but alpha h double dot. So I can replace alpha as h double dot by r. So this comes from the assumption that it's a pure rolling. So 2xr 3 by 2 m r square. So alpha is h double dot by r. So r gets cancelled and r gets cancelled throughout. So minus 4kx r. Okay, r gets cancelled throughout, minus 4k m h double dot. Okay, so that is the thing. Okay, 4k and here you have 3k. So h double dot, you have shown that it is 4k by 3m x. So this is your omega m, because acceleration is, it undergoes a simple harmonic motion where acceleration is directly proportional to your displacement and the constant is your natural frequency. Omega n is 4k by 3m. Okay, the answer is 4k by 3m. Answer is C. Though we have taken a long time, but you should understand each of the important steps in this, because this is a general process which can be applied to finding out the natural frequency for problems involving disk. Okay, so when you have disk and when you have a combination that it rolls without slipping, this is the shortest way which you can do a problem. You can use energy methods also, kinetic energy plus potential energy, some of them is constant, so you can use that. You can write down the kinetic energy half mx dot square for this problem plus rotational component half I naught omega square. Okay, and the potential energy comes basically because of the spring, so that summation of that, it's constant, so you differentiate and relation. So ultimately you have to get a relation between the h double dot and x. Okay, so always any kind of problem you have to end up getting an equation between the acceleration and the displacement, and then only the proportional constant in natural frequency, so you end up getting natural frequency. So this is the most robust way. So two kinds of method exist, force method or energy methods. So what we have discussed is the force or the moment method, and the energy method I have told you just briefly how to solve it. So the answer is root 4k by 3m. Thank you.